Today we are explaining MemHarness memory as reconstructed, not replayed.
What problem with agent memory is this paper trying to solve?
Language model agents often retrieve a successful past experience and paste it directly into the current prompt. The problem is that a memory can be relevant to the task while still being wrong for the current state. A historical instruction may assume a different room, a different object location, or a different shopping constraint. Replaying it verbatim can therefore cause negative transfer.
So retrieval relevance induction level usefulness are not the same thing?
Exactly. Explicit memory banks are easy to inspect, but they usually treat memories as fixed records. Parametric memory can adapt its behavior, but the original experience becomes difficult to inspect or revise. MemHarness targets the middle ground, keep the experience attributable, then adapt it before it influences the next action.
What does the new pipeline do between finding a memory and taking an action?
It adds contextual memory reconstruction. The same unified policy first retrieves a small set of experiences, compares each one with the current situation, and rewrites useful information into state-specific guidance. If a memory does not fit, the policy can reject it and fall back to its own reasoning. Only then does it generate the executable action.
Why does the method need the memory's original situation, instead of only the retrieved advice?
Because the original situation tells the policy what the advice was conditioned on. Comparing that source observation with the current history lets the policy distinguish a transferable principle from an instruction whose assumptions have become false. This is the concrete check that static replay is missing. The retrieval step can be written as E sub t equals R of Q sub t and B, with the retrieved set containing K experiences. In plain language, the policy forms a query from the current decision and selects a small number of memories from the bank. This equation defines what enters the reconstruction stage. It does not yet decide whether any memory is safe to use.
How is the reconstructed guidance trained when there is no label saying exactly what the rewrite should be?
The guidance is latent, so the authors train the whole retrieve reconstruct that chain with group relative policy optimization, or GARPO. The policy samples groups of trajectories, compares their task rewards within each group, and sends that relative signal back through the reasoning, reconstruction, and action tokens. Successful task behavior therefore teaches the policy which memories to preserve, rewrite, or discard without human reconstruction labels.
What happens when the method is compared with ordinary reinforcement learning and static memory systems?
On ALF World household tasks, on webshop shopping tasks, it reaches 75.6%. These are the best results in the reported comparison, exceeding both pure reinforcement learning agents and memory methods that inject retrieved records without this reconstruction step.
Does the gain really come from reconstruction, or simply from adding a memory bank?
The oblations point to reconstruction. Removing it makes replay harmful, while replacing the internal reconstruction module with a generic Q into 0.57b instruct rewriter drops ALF World from 85.2 to 77.7%. So zero-shot rewriting is not enough. The adaptive module has to learn from task rewards together with the actor. The training dynamics plots show how the policy uses memory over time. ALF World settles on sparse retrieval, with only about 2 to 3 retrievals per trajectory. Workshop keeps retrieving more often, but continues filtering the retrieved guidance. In both environments, trajectories with accepted reconstructions have higher success than trajectories with rejected ones.
Is this filtering still useful when the environment changes after training?
Yes. In ALF World's out-of-distribution setting, room layouts and object placements are unseen during training. MemHarness reaches 85.9% average success, compared with 76.3% for reinforcement learning plus raw memory. The intrinsic policy without memory reaches 83.0%, while unadapted replay falls to 82.4%. The comparison shows why memory must be filtered before it is trusted. The final mechanism check changes a current state, while keeping the retrieved memory fixed. Small counterfactual edits make the policy adapt or reject the memory more often. Removing the historical source state leaves rejection rates unchanged but lowers ALF World from 85.2 to 80.0%, showing that the source context is needed for useful acceptance decisions.
What is the main conclusion to carry away?
MemHarness changes agent memory from retrieve and replay to retrieve, evaluate, and reconstruct. Its unified policy keeps memories inspectable, compares their source situations with the current state, and learns through GARPO when to adapt or reject them. Across ALF World, workshop, ablations, and unseen layouts, the evidence says that the reconstruction step is the source of the robustness, not retrieval by itself. That wraps up this paper workflow.